from this computer. Good. So we're recording now, and we're gonna go to Wiley Plus site. Log in. Chapter. Wait, is that the right one? I don't think that's the right book, right? Yeah, that's no. Oh yeah, that's the right one. Well, 21. More students coming. Go. We did magnetic fields, force the magnetic field on a moving charge. Don't forget, a moving charge produces a current, right? So what you see right in here is not much different than what you see right in here, okay? Motion of charged particle in a magnetic field, the mass spectrometer, but before the mass spectrometer, we also covered the velocity selector. I didn't see the velocity selector here in your book, so you gotta rely on the notes that I have here for the velocity selector. Force on a current, okay, and the next gonna be the torque on a current carrying coil, on a current carrying wire. Okay, magnetic and okay, we're not gonna do magnetic materials, okay? So let's start with 21.6. 21.6 torque in a current carrying coil. Let's put this current carrying coil. More 21.7 is going to be what? Magnetic field produced by current. Oh, very important. Magnetic fields produced by a current. That's a law of physics. Law of physics, okay? So the source for the magnetic field is a current. And 21.8. Let's go back here again. Ampere's law, another law of physics. Ampere's law, another law of physics. But let's start with those. I'm gonna boldface what we haven't covered yet. 21.9, skip. We're not doing 21.9. Okay, in order to see the torque in a current carrying wire, you have to be very patient, okay? And look at the forces in a current carrying wire. You can, in order to see that, you have to do drawings. There is no doubt about that. And you have to account for every magnetic force that is in that coil, in that loop. Not just, let's not call it a coil, let's call it a loop, in a current loop. I think it's better, current loop. The loop can be made of a single coil, made of a single coil, made of a single coil or more. Okay? Torque in a current carrying loop. Loop is a better word for that. A coil implies that you have more than one turn. So I prefer to use a loop. Now let's get the magnetic fields here. Okay, so here is my loop. Torque in a current carrying loop. A current carrying loop. So try to visualize, and I'm gonna break this drawing in simplify it, right? I'm oversimplifying this drawing, and let's see, let's start with the magnetic field. Let's start with the magnetic field. So this space is filled up with a magnetic field into the board, this whole space. I'm not gonna draw all the lines, okay? Space filled up, space filled up with a B field. Like that. And what else do we do? Filled up the B field means we have a B field all over here, not just at this point, but all over this plane that you see right here. Add conducting loop. Add conducting loop. And here's my conducting loop. Right here. Okay. Power conducting loop. I'm not showing the power supply there. I'm just telling you that we have a power supply there powering this loop, this current loop. And when we do that, we create a current around the loop. 1, 2, 3, 4, like that. Okay. And I am also naming each branch of the loop. Name each branch of the loop. Okay, so here you go. Here's gonna be branch number 1. That's why I put current I1. This is gonna be branch number 2, 3, and 4. Okay, so here you go. Number 1, 2, 3, and 4. I put in different colors to make it easier to identify it. Do you follow that? You know, visualize that somehow we have a power supply here, a battery that I'm not drawing for simplicity's sake, and is powering a current. The current here is equal to this current, equal to this current, and so on. And I'm going also to document the thickness of the loop. And one more thing, this loop is not in the plane of the, so I have add conducting loop, not in the plane of the screen. Okay. So, and you're going to understand what I mean about that. Loop is not in the, this loop is not in the plane of the screen. Okay, so here is my loop, right? 1, 2, 3, 4. right? The loop is kind of out of the plane of the screen. It's making an angle with the plane of the screen. And that that's why I put this X and Y before. See here. Yeah, actually it's like that. Sorry, folks. This is A and this is gonna be B, okay? B lengths. A and B. The B doesn't look like exactly B, right? It looks like a projection of that. It should be the B cosine of theta. And I have to name it here. A. What you see right now, and I'm gonna make a drawing slightly different than what I see here, than what you see here. Here is the plane YZ, okay? Axis into the board. Okay, let's do that again. Here, B field into the board, a loop that if the plane of the loop does not coincide with the plane of the screen, it's going to be something like that. That's the plane of the screen. If you here you go, here's the loop, right? Here's the loop. 1, 2, 3, 4. Instead of coinciding with the plane of the screen, the loop is a little bit inclined. Okay. So here you go. We have we set a current around the loop. We have branches 1, 2, 3, and 4. That's the length of the one of the sides of the loop. Because this loop is not in the plane of the screen. Because this loop is not in the plane of the screen. Okay, so what we're going to have, we're going to have a side here. That's going to be B cosine of theta. B, oh, he always does that. Cosine of theta. Combo. B cosine of theta. Okay. Looking sideways. Let's see here. Okay, this one is gonna be right in here because we still need this YZ plane, right? We're going to need the YZ plane in the other drawing as well. More students coming. Why do I have A here? I shouldn't have A here. Let's see if there is any other. Yeah. And now if you look sideways, you rotate the plane, right? The Z axis is into the board, so the B is pointing in the same direction as the Z axis. the direction of the x-axis in the same direction of the x-axis, right? The x direction is given by the right-hand rule, y crossing with b into the board. And now I'm gonna look from the right. Okay, I'm gonna rotate this guy here from the around the y-axis. I'm gonna rotate around the y-axis. Okay, and the x-axis is going to appear. And now you see exactly how the loop looks like sideways. Remember I told you that there is an angle theta there, right? We need to do all of that to understand this, the forces acting in the loop, in the current loop. Okay, I put the theta here at this point. Let's see if we, let's see here. Yeah, if I use the theta here, so it shouldn't be cosine, it should be sine, okay? If I account for the theta in that direction, then it shouldn't be cosine, it should be sine in there, okay? So the B sine is this length right in here. And let's not forget, right? Let's not forget that's the B length. And I'm going to transfer this guy there. So that's B. And this one here is going to be theta. And what we see is only in that other view, right? In that other angular view is just the B sine of theta. And now, here you go. We see like that. Okay. Now let's start accounting for the forces acting in this loop. Let's start accounting for the forces acting in this loop. So what's happening here? The top branch of the wire is wire number 4. The bottom one that's coinciding with the 4, so you cannot see behind, is going to be wire number 2. Okay, I can even put that with this color and make it thicker so you can visualize the wire better. The green one is just behind this one that you can barely see because it's aligned, right? Lined up. I'm gonna send it to the send to back. Yeah, I'm gonna put it at the color green here for you. No, not this one. It's this one here. Okay. This one here is gonna be red because, right, better. We're gonna fill this red. And this other one here is gonna be black. Just like the number 1 is black and the I3 is black. It's already black, right? So I don't need to do anything. Okay? Did you get the idea? All right. I'm going to display that to you here. How it looks like. And I'm going to stop sharing the screen. Remind me to share the screen again so you can see from my. Somebody's talking? I'm going to display that. Here you go. Here's my loop, okay? Let's see. Initially, the loop was like that. 1, 2, 3, and 4. Okay? Consider the edges of this book as the edges of my loop. When I loop my loop sideways, it's going to be with a little with a little angle theta, but this theta is this angle theta here, okay? That's gonna be the plane of the screen that you saw before. And now you're looking at the axis in the other direction. And what else? What else? We have the current coming towards me at this edge. The current going down I4 on this side here facing me. The current I1, the current I1 going down here, and there is a mistake here. Let me correct that. It's I1, not I3. Okay. I2 is behind I4, and we have the current flowing this way. For simplification purpose, I'm doing just a single loop. Okay, well, if you have more than one loop, it's not going to be difficult to, all you have to do is multiply the final result. Okay, let's see if I have a problem here. I1, I2, yeah, I1. That's good. More students coming, go. And now I'm going to account for every force in my loop. I'm going to account for every force in my loop. And I'm going to go back here, share the screen again. Okay, we are going to use the, let's, okay, here you go. We will have to cross. Don't forget, in this case, this guy is going to be red as well. Let's see, red. This one should be red as well to make it, yeah, better. Okay, now I have it in the way I want. I will replace this one here with the red. Okay. And to back. And now we are going to cross the current with the magnetic field, right? So you gotta do your right hand along the direction of the current 3 and cross towards the B field. So the magnetic force is upwards. So that should be F3. That should be F3. Okay? We do the same for the other wire. Palm along the direction of the current, cross towards the B field, consequently, the force is downwards. Okay? And now look what we end up getting. We are going to get a component of the force that is along the direction of the wire. The wire is rigid. So this force here, and we have the same force, contrary force, right? Trying to stretch my wire because the wire is rigid. It's not going to give. The wire is not going to give. This component that you see here produces no torque whatsoever in the wire, whereas the other component produces a torque. Okay? Produces a torque. So let's see if we have a drawing here. Can you see the torque being produced here in this wire? Okay, F3 and F1 produces a torque in this wire. That's going to be given by something like that, torque. And I will put a Starting position, format. I don't. I'm trying to put an arrow here to this guy. There's a way to do that. I can't seem to find it. Format shape, size, and position. Let's see. Line must be this one. Yeah, that's the one. Let's see if it's the right direction. Yeah, but it's okay. So that's the torque that F1 and F3 are exerting on the loop. I want my arrow a little bit larger than that. Let's see if I can do that. Yeah, I can do that. Torque. Okay. And this torque is going to be what? It's possible to write down the value of this torque. Okay, it's possible to write down the value of this torque. It's going to be F3. Let's see here. That's going to be this one here is theta. This angle here is theta, right? I'm going to get this one up in there so you can see it more easily. This angle here is theta. This one is 90, and this one, okay, theta plus 90 plus this x angle here that I do not know, right? It must be equal to 180. So this angle here must be 90 minus theta. If this is 90 minus theta, this one is going to be theta. Okay. If this one is theta, then the component that's applying the torque is going to be F3 cosine of theta. Do you see that? And you have the same thing here. We're going to write down everything there in the notes, okay? And now we are going to see whether the currents in the other two directions produce a torque in the loop as well. Okay, here you go. Here is the force on wire 4. Here is the force on wire 2. Okay, current cross B is towards you, and this other one is away from you. So this force that you see right in there is trying to stretch the wire, but it's not producing any torque whatsoever. Okay, F2 and F4 does not produce any torque whatsoever in the wire, in the loop. Okay, so let's document everything that you said so far. Torque in a current carrying loop, right? Here you go. Okay, torque loop has 4 arms. Arm 1, 2, 3, and 4. Arm 1 and 3 have length A. Arm 2 and 4 have length B. Arms 1 and 3 are perpendicular to the B field. Let's take a look here. Yeah, it's perpendicular. Arm 1 and 3 are perpendicular to the B field because 1 and 3, 1 is towards you. It does make an angle with angle 90 degrees with respect to B, and arm 3 also makes an angle of 90 degrees with respect to B. Magnetic force applied to arms 1 and 3 is IAB, right? ILB, current, length, and B. magnetic forces applied to our arrow opposite in direction. Net force is equal to 0. They have the same intensity. Magnetic force applied to arm also makes an angle. Let's see here. Magnetic force applied to arms 1 and 3. I don't want to write like that. Has a net torque. Oh. 1 and 3. Okay. I'm mixing up here. Sorry, I meant. Here you go. I'm mixing up here. Here you go. That's 1 and 3. Arms 1 and 3 make an angle of 90 degrees, right? So this one applies a torque to B. Okay, so magnetic forces applied to arms 1 and 2 has a net torque different of 0. Torque of arm 1 and 3 are in the same direction and reinforce each other. Two and 4, let's see. I'm mixing. Net torque different of 0. Net torque different of 0, yes. And the torque is going to be given by net torque is going to be 2IA B sine of theta. Yeah, like that. Arms 2 and 4. Yeah, arms 2 and 4 make an angle, that's right, theta with the B field. But the force is going to be perpendicular to the B field, but the net force is going to be equal to 0 with a net torque equal to 0, okay? Is 0. That's what you have. And now what's going to happen? You know, once you have a magnetic force pointing up here, this magnetic force is going to apply a torque that's going to make the loop oscillate back and forth. Okay? Unless you do something else. You can do that. And there is a very nice simulation on this type of phenomenon. I'm going to put the link here. Simulation of current loop inside a uniform magnetic field. Let's take a look at that. I like the simulation a lot. Okay, so here you go. Here's my loop. And let me see if I can pause it now. Here you go. Okay, here is the arms that produces this arm, and this arm produces a torque in the loop. And here are the other two arms that do not produce a torque. There is a force, there's a magnetic force trying to stretch this loop in this direction. One magnetic force in this direction, another magnetic force in this direction. But there is no torque applied by those two forces here at the other edges, right? But there is a torque applying here to this guy. Okay. Let me see if I can change. Okay, it's changed the direction. Okay, good. So that's what happens. And now here they do something else. Notice that this loop is not oscillating back and forth like I mentioned to you, right? And there's a reason for that. The reason is that, you know, in order to make this loop a practical device, we must make it rotate or go a full rotation around its axis. Okay, and there's a little trick that we can do to do something like that. I'm gonna make it. Here you go. Take a look. Watch out. Watch the direction of the current here. Okay, the direction of the current in the loop. You're going to see what's going to happen. Do you see here the direction of the current right here in this arm is pointing from the left to the right, right? And look what happens, you know, in the next few moments, in the next few seconds, right? Oops, at this very moment, something is happening to the direction of the current in this loop. What is happening? See, do you notice that the current inverted the direction? The current inverted the direction for a very important reason. The current inverted the direction to make the loop go a full rotation. A loop that just oscillates back and forth is that loop in which the current doesn't invert the direction. But a loop that oscillates back and forth doesn't have much of a practical use. If you want to have a practical use for this type of loop, you want to make it go a full rotation around its axis. And in order to do that, you must invert the current at a given instant of time. And that's exactly what this loop is doing, okay? Here you go. Let's take a look. Watch this arrow right in here. I'm going to turn off the magnetic field, okay? Watch out, and I'm also going to turn off the Lorentz force, okay, the magnetic force. Do you see these arrows pointing from the right to the left? Look what's up. The current is inverting the direction right now. That's why you don't see the direction of the current. And let's see, now it's pointing from the left to the right, okay? So this is the principle of the electric motor. This is the principle of the electric motor. And what you have right in here is called a commutator. It's not difficult to do something like that. Okay, the commutator is there to make sure that the loop rotates in a single direction and doesn't keep on oscillating. Okay. So I'm going to, I have everything explained here in my notes that I'm going to document for you. Here you go. Okay, so here you go. An electric motor consists of a current loop, subject a uniform B field. In this device, you have 4 arms, 1, 2, 3, 4. All 4 arms are subject to a magnetic force. The magnetic force depends on the following: the current value, the magnetic field, the size of each corresponding arm of the loop. The angle that the area vector of the loop makes with the magnetic field as well. Okay, that angle that you saw. Here you go. The force on arms 1 and 3 is given by this value here. I'm going to even make it so it's very clear, right? Force of 1 in arm 1 is equal to force in arm 3. I'm going to do the same here. Force in arm 2 is equal to force in arm 4. Okay. Since I, L, and B are constant, then the force will depend only on the angle theta, The net force between arm 1 and 3 is 0. Between arm 1 and 3 is 0. And then I'm just going to repeat that. The net force between arms 2 and 4 is also 0. It's also 0. However, when it comes to the torque, the story is different. For arms 2 and 4, the net torque is 0 because the pair of forces is collinear with each other. One is pointing in this direction, the other is pointing in this other direction. They're collinear, and consequently, they don't produce any torque. Whereas the other two, okay, they're not going to be collinear, see? They're going to be parallel to each other. And that makes the difference. When we have a situation like that, here you go, when you have a situation like that in which forces are not collinear, you end up producing a torque. Are not collinear all the time. For this reason, the net torque due to these two arms is different. The torque becomes zero when the two forces get aligned with one another. Okay, just like in the simulation right in here. Let's turn on the Lorentz force. So here you go. Resume. Right? So here you go. The forces are not collinear. They're not collinear yet, but they are going to become collinear right in here. Right in here, they become collinear. That's why you don't have the force vectors there. Okay, and as the loop keep on rotating, the forces are no longer collinear and keep on producing a torque. But the forces on those edges here, they are collinear all the time. It is this torque that makes the entire loop rotate with a given angular velocity that varies the angle theta. Okay? Throughout this rotation, the torque varies from a negative value to zero until it reaches the maximum value. Okay, and you can under those conditions, okay, under these conditions, the loop just oscillates back and forth. Unfortunately, this type of motion is not useful at all. In order to make our loop a useful device, we must make it rotate. We must make it complete a full rotation. This is done by inverting the current at the instant of time when the torque is zero, or when F1 and F3 are collinear with each other. Okay, that's the whole story of this device. Okay, a device like that, a device like that, a device that behaves like that is an electric motor, which is the principle of many devices that we see out there, like the blender, your blender that you have there at home. Okay, it is, you just have an electric motor there inside that makes the blades rotate in a single direction. Okay, and that's what we have for this story here. There are more. Okay, go. Here's the rotation, right? At this point in time, the two forces F1 and F3 are collinear with each other. Consequently, there is no torque whatsoever. You see tau equals to 1 here. And then a little bit later, because of the inertia of the loop, remember the angular velocity of the loop is different of zero, it's going to overshoot the situation, right? And the torque is going to become different of zero again, right? so it goes. Okay. So that's the story we have for the loop, current loop, and now we can start talking about sources of magnetic field. The question is, what produces the magnetic field, right? That's the question that you have to ask yourself. What produces the magnetic field? Okay, back in 1820, notice that those developments happened mostly during the 19th century, okay? It was during the time that Thomas Alva Edison was alive. Okay, so the question is, what produces the magnetic field, right? I call it, what's the secret sauce of the magnetic field? I like to call it this way. What's the secret sauce of a B field? We know that there are B fields around, the Earth generates a B field, the Earth has a B field, the Sun has a B field, the other planets, many of the planets have a B field, lodestones have B field. Mars, the planet Mars doesn't have a B field. The Moon doesn't have a B field, but most of the planets out there has a B field, a magnetic field. So what is generating a magnetic field? Okay, that's something that was discovered back in the 1820s. There was this guy called Ørsted, William Ørsted. Let's take a look at him. That he discovered that electric currents produces a magnetic field. Okay, it's an electric current that produces a magnetic field. Let's take a look at Ørsted. Ørsted. Here you go. No, it's not William. Hans Christian Ørsted. Actually, Hans is in English is William, right? Let's take a look here at Wikipedia. Okay, Hans Christian Ørsted was a Danish physicist and chemist who discovered that electric current creates magnetic fields, which was the first connection found between electricity and magnetism. This is a law. This is a law of physics, okay? This is a law of physics. This is a law of physics. Okay, now we have three laws of physics. Let's go get our equations here. I'm gonna use this one here. The first one, okay, the electric flux is equal to a charge enclosed by a Gaussian surface divided by epsilon naught. That's the first law that we saw. Coulomb's law, right? What is in the left is the flux, electric flux enclosed by the Gaussian surface. And this one is easy. The magnetic flux is equal to 0. And now we have this other law that states an electric current. And first I'm going to spell that out in words, okay? Creates a magnetic field. I'm gonna okay. Oh, there's one more law here, right? The magnetic force is equal to Q V sine of theta. There is the other one here. And then we have this other law. An electric current creates a magnetic field. Let's take a look. And that's called Ampere's law. Yeah. So it's also Ørsted that discovered that, but Ampere's got the credit for that. Unfortunately. Okay, the direction of the magnetic field, in this case, the direction of the magnetic field, those are just the qualitative ideas, okay? The direction of the magnetic field is determined by the right-hand rule applied in a different way. Okay, and here the step-by-step. Here you go. How to find the direction of the B field? I'm gonna do an example here very soon. Extend the palm of your right hand and orient the right thumb in the direction of the current. The direction you rotate the palm of your right hand is the direction of the B field. Okay? Let's stop sharing again so you can see me better. I'm going to stop. Let's see here. Here you go. Here is the direction of my current, right? The current is in the direction of the tip of my pencil. So the current is pointing in this direction. So in order to find out the direction of the magnetic field, you point your thumb in the direction of the current and circulate the palm of your hand, of your right hand. And that tells you the direction of the magnetic field. Okay? The magnetic field circulates around a current. Okay? We say that the B field circulates around the current. Now, in the case, whereas for the electric field, compare that to the electric field. The electric field, whereas the electric field radiates away or towards the source, towards its source, the charge. See the difference? B fields circulates around its source, which is the current. E fields, see the difference here? E fields points towards or away from its source, electric charge. Point. Circulate, right? Let's take a look at our book, right? Here you go. Here's the torque and the current carrying wire, right? You did the same thing that I did here in the class. Now let's take a look at the law discovered by Hans Christian Ørsted or William Ørsted, which was given the name of Ampere, unfortunately. Here you go. That's the experience that Ørsted did at the time. He had a current carrying wire in the vertical direction, connects to a battery, of course. And he put magnetic compasses around it here. He didn't expect what he got. What he discovered? He discovered that whenever he turned on the battery, the needle of the magnetic compass would orient in those specific ways here, like it was circulating around the wire, okay? Just according to the right-hand rule. Okay, there are some magnetic fields that I'm going to tell you how it works, right? There's a relationship for the magnetic field for given configurations of currents. And here you go. For the magnetic field of the long straight wire, infinitely long straight wire, is going to be inversely proportional to the distance from the wire. And because the source of the magnetic field is the current, the magnetic field will always be proportional to the current itself. We can write down like that. So here you go, just like it is in the book. The magnetic for infinitely long straight wire is proportional to the current and inversely proportional to the distance from the current. Specifically speaking, it's going to be like that, mu naught I 2 pi r. So the constants are mu naught divided by 2 pi. This mu naught is the magnetic counterpart of our epsilon naught that we saw before, right? Magnetic counterpart of the dielectric constant. And there's a name for that. It's called the permeability of free space, vacuum. Recall that a parallel plate capacitor produces a uniform electric field. Well, folks, we have the magnetic counterpart of the parallel plate capacitor. Its magnetic counterpart, by the way, is the solenoid. Have you heard of the solenoid? We have solenoids in our car. It's the solenoid, which produces a uniform B field inside it. Okay? In the case of the solenoid, let me show you how a solenoid looks like. Okay, here you go. Here's the relationship for the magnetic field of the solenoid is directly proportional to the current and directly proportional to the number of turns of the solenoid. The solenoid looks like something like, let's see, I have a solenoid here for you. Here's the wire. Okay, here's the solenoid. Okay. You get a tube, get a power supply, connect your wires around into the power supply and around the tube. When you power the solenoid, you're going to have a current circulating around the solenoid. And each of those wires here is going to produce a current. And the current inside the solenoid is going to be uniform. Can you remember that? We represent the solenoid in this way here. Current coming out, current going into the screen. Okay? And it's 9:56. Let's see. Oh, yeah, thank you. Thank you, Lizelle. I forgot completely. So here you go. What did I miss? What did I miss, huh? Let's go back here to the notes, right? I believe I stop it here. Okay, extend the palm of your hand around it, right? And B field infinitely long straight wire is inversely proportional to the distance, directly proportional to the current. Every magnetic field is going to be directly proportional to the current. Every, no matter what, no matter the configuration of your current, comma, the it's magnetic, no matter the geometrical configuration of your current, its magnetic field will always be proportional to the current. It's going to be something like that. It doesn't matter if it's a solenoid. It doesn't matter if it's a straight wire. It doesn't matter if whatever crazy thing you want to, whatever crazy geometrical distribution that you want to have for your current, it will always be proportional to the current because that's the source of your magnetic field. And then if we look at every specific configuration, like infinitely long wire, right? It's going to be like that. And here's the solenoid. Here you go. Here's the solenoid here. That's what I mean by solenoid. The wires turn around this tube, completing a circuit and producing a uniform magnetic field here inside. Okay? So now it's 9:59. Let's take a little break, but before we take a little break, let's take attendance. Today is the 20th of March. 20th of March, lab 4. Okay, Jacqueline Arieta Hernandez. Are you there, Jacqueline? Thank you. Next is Sky.
Here.
Did you say something, Sky? Sky
I'm
said,
here.
right? Yeah, okay. Your voice was so clear that I thought she was here in my room, not in the speakers, you know? I was a little bit taken aback there. Your voice was so clear, but so clear that it looks like it came from behind my back, not from the speakers. It was really a weird, weird feeling. Thank you. Ashley, are you there? Let's see if Ashley is here. I don't see Ashley in my list. Next is Corina. Thank you, Corina. Norberto Lopez. Thank you, Norberto. Vanessa Mena.
Here.
Okay, thank you. Yorgo.
Here.
Thank you. Giselle. Thank you. Next is Paul Zapata. Good. And then we have what, 7 students? No, we have 8 students. Okay, yeah, good. So let's take our break. It's 10:01 right now. Break from 10:01 a.m. to 10:16 a.m. And I see you in 15 minutes. And by then, you're going to have your spreadsheet there in your group folder. Okay? So see you soon. Okay, I'm back here. And that's going to be today's lab number 4. And lab number 4. And by the way, let me tell you what I did, right? I corrected lab number 1 report, no? The report for lab number 1 and uploaded the correction to your group folder, okay? And I want you to check there, and I need to, my students who took the course first with me, they know how to open that document, but many of you still do not know, right? Let me see if I can get the instructions here. Let's see. There's some instructions that you need to follow to see your grade. See if I can find the instructions here. Well, let me do that on the fly. I have it written somewhere. Okay, I correct the report for lab number 1 and upload the correction to your group folder. I will be correcting the report for lab number 2 in the next few days. Report for lab number 3 is due now, right? Make sure you upload your report, and to see your grade, the grade of the report of lab 1, you must do the following. Here you go. A. Download. You go. Oh, I need to start the. Thank you. Thank you again. My fault recording. Okay, we're recording. Here you go. Lab number 4. But before we get into lab number 4, right? I was saying that I corrected the report for lab number 1 and upload the correction to your group folder. I'll be correcting the report for lab number 2 the next few days. Report for lab number 3 is due now. To see the grade of the report of lab 1, you must do the following. Go to your group folder. B. Download. Let's see. Let's go to your group folder. Am I sharing the screen, by the way? Yes, no? Let's see. Right in here. Right? When you go to your group folder, make sure you look for the HTML file, P07L01G, right? Group number. And also look for the folder associated with this HTML file, okay? So I'm gonna go to your group folder, and I cannot correct that. Cannot copy it, strange. Okay, so go to your group folder. Go to your group folder and look for P07L01 group number .html file and the folder. Okay, P07L01, P07, and the folder files. Not one, right? I'm gonna put X here. Oh no, that's, or I already have X there. Here you go, files. So in the case of group one, the file is this one, HTML file is this one, and the folder is this one here. P07L01, and group number 2 is the same thing, right? HTML file, lab01, group 2, and the folder, the associated folder. Group number 3, same thing, P07L01, HTML, and the folder. Okay, download both the HTML file and its folder to your hard drive. Okay.
Professor, won't the grades just be in Canvas or no?
It will. I didn't post in Canvas yet, but I will do that. Okay. I didn't post in Canvas yet, but I'm gonna do that. I didn't have time to post it on Canvas. And down, okay, let's see, unzip. When you download those two files, let me show you what happens. I'm gonna download those two, okay? Group number 3, here you go. Download. It's gonna zip those two files and it's going to download to the download folder. Here you go. That's the one. No, not this one, is this one right in here. 1025, yeah. Okay, it's zipped. Okay, the file is zipped. And zip, download both the HTML file and its folder to your hard drive. Okay, look for the downloaded files in your download folder. Okay, D, unzip this file, the file and folder. How do you do that? I'm going to unzip it. All I have to do is to double click in this zip folder, and then here you go. We have the file and the folder. Okay. Copy the HTML file and the folder. You gotta take it out of your folder. Copy into the same folder. Okay. Here I just click it and drag both of them. Do not drop this file here on the folder. Do not drop it. It must be outside this folder. This folder works together with this file. Okay. So here you go. Unzip the file and folder by, if you look the download, let's put it this way, double click. I'm going to put it this way, double click the zip folder with this, double click the zip folder. Okay. Inside the zip folder, copy both the HTML file and its corresponding folder. Paste them in another folder, of your computer. Make sure that the HTML file It's outside its corresponding folder, okay? It's outside. I'm gonna highlight that boldface italicized. Double click the HTML file and you will be able to see your grade and be able to see the correction, right? To your report. The correction to a report in color code. The grade is at the top of the file of the window. Okay, so those are the steps that you have to take to see what you missed and what your grade was. Let's see. How to consult your grade and your report grade and correction. And now we can go to lab number 4. I'm going to be doing this same procedure for all the remaining corrections, okay? Lab number 4 now. For yeah, first I have to upload your lab 4 right here, and then I will brief you what the experiment is all about. Let's see, where is that? This one? No, it's not this one. Group folder, here you go. Okay. Group 1. Oh, before we go there, let's make sure first that everything is fine, no problems here with my files, right? Every now and then I see a little bit of thing that I left behind. I don't seem to have any problems here. Okay, that's how your spreadsheet should look like. Okay, 8. That should be 4. No problema here. Another one, 6, 7. 8, 3, 5. 1. Okay. Okay, so that I need to close this one, and now I can upload those files to your group. Group 1, download the file for lab number 4. Group 2, download the file for lab number 4. Group 3, download the file for lab number 4. Lab 04, okay? Please, please download your spreadsheet, lab 4 spreadsheet, lab 4 spreadsheet from your group folder. Okay. The goal of this experiment, is to verify Ohm's law. To verify Ohm's law. Okay. We will be using the simplest circuit you will ever see in your life. Okay? To verify this law, we will be using the simple circuit you will ever see in your life. Okay? And let me get lab slides here. Yeah, this one here. Okay. So we start with a power supply. Here's I drew my power supply like that. Okay. So we start, I'll close this one as well. And start with a power supply, your fancy battery, okay? The battery that you can change the voltage, your fancy battery. And I'm gonna, while I do that, I'm gonna put a list of equipment here. List of equipment. 1, power supply. I'll put it separately. Okay, and then the power supply has a positive jack and a negative jack. Red and black. Red positive, black negative. Okay. So red cable with banana connection. Unfortunately, we do have one of those there in the banana termination. Okay, banana termination. Here you go. That's how those cables look like. I believe I showed that to you before, right? That this connector here is called a banana. So red cable is banana termination. Or supply. Connect red cable with banana termination into the red jack of the power supply. Okay. Let's see. Let me do it differently. I forgot to do something here. Here, let's start with the list of material, okay? Let's start with the list of material. That's easy. Here you go. Here you go. That's the list of material. You're gonna use one resistor. I forgot the resistor here that you're going to use, okay? One resistor, a digital multimeter, a power supply, right? Two black cables and two red cables, not banana, yeah, banana plug or banana plugs termination. Banana plug termination. Okay. Before you start with the power supply, first measure the resistance with the resistance of the resistor with the DMM. Okay, that's what's missing here. Yeah, I didn't put that in my. And now we can. That's the step that was missing. Okay, connect the power supply. Power. No power supply. Connect red cable with banana termination to the red jack of your power supply. Next, connect the other end of the red cable to the resistor using an alligator jack. Okay, there is let's see if we have it. I want to show you how those alligator jacks look like. So you know I'm talking about alligator jack. Clip, not alligator jack, like alligator clips. Okay, here you go. That's how those alligator clips look like. Here you go. Sometimes they sell the cables with those alligator clips there already, right? And then they also sell those alligator clips so you can connect it to the banana termination of the cable. Okay? The banana termination goes exactly here, right in here. And that's the clip that you can open it and clamp into the end of your resistor. Connect the other end to the resistor using an alligator clip. Better. Back cable with banana termination. Connect with the black plug, black jack. Okay, not plug, black jack of the power supply. Okay. Connect the other end of the black cable. Black cable to the free end, to the remainder free end of the resistor using another alligator clip. We have our circuit ready here. That's how it looks like. Let's see if we can get in the internet. Circuit with a power supply and a single resistor. Let's see if they have it here. Let's see here. Let's take a look at this one here.
This instrument right here is called the triple power supply, and it's called that because it's 3 power.
So here you go. Here is one power supply available out there in the commerce. Okay. Do you see the banana cable here? Plug it into the jack of the power supply, the red one in the red termination, the black one in the black termination. Let's see if they have the.
There's an output here, output there, and an output there. This one's fixed at 5 volts, and this one's adjustable, and that one's adjustable.
Now let's see if he has the resistor here. Let's keep
The
on
nice
playing.
thing is the adjustable ones will tell you what the voltage is. It's 5 volts and the current. And I can turn the knob and change.
Like I said, we have something like that at LA Harbor. It's not exactly this one here, but it does the same job.
Change that 8 volts.
Oh, do you see the alligator clip here? Here, the alligator clip. You know, they have cables with alligator clips already fixed in there, but they also have alligator clips, free alligator clips that you just plug into the banana termination.
Back down to 5 volts. And the current meter is at 0 right now because there's an open circuit. And we can see there's 2 wires coming off of it. So these wires plug in to.
Note that this end is the banana plug, and this other end is a different type of end. It's not exactly alligator clip, okay, but it also works. There are different types of terminations out there in the market. I like to use this one as well.
The inputs. I put the black one on the negative and the red one on the positive right here. And there's an open circuit. There's nothing connected across there. And you know, if there's an open circuit.
At this point in time, we have an open circuit, and because we have an open circuit, there is no current flowing through the circuit. Okay, what we are going to do, we are going to put the resistor right here at these two ends.
No currents flowing. I could short circuit those.
Yeah, here you go. You are short. He's shorting circuiting it.
That's because the power supply is not ideal, but nothing's really ideal in the real world. But it does try to maintain.
Note what happened when he short circuited. While the circuit is open, the amp is 0. It's exactly 0 because the charges cannot jump from one end of this termination here to the other one. Okay. However, when he short circuit the power supply, it's not recommended to do that. Okay.
I could put a resistor.
But he did anyway.
So this is a resistor right here. It's a very
it's a 20 watt resistor. Let's see. We gotta go back here.
Let's try to maintain a constant voltage. 0 on the current.
Okay, that's the one I want to show you. Here you go.
No currents.
He's gonna short circuit. When he short circuit, what happens to the amp? What happens to the current? It goes very high. 3 amps. 3 amps is a very high current. Okay, the voltage decreased. The voltage decreased because there is no resistance between those two guys, right?
You can see the voltage goes to the 0 and the current peaks out. That's because the power supply is not ideal, but nothing's really ideal in the real world. But it does try to maintain a constant voltage. And I could put a resistor across it.
He's using a 5 volt power supply right now. The power supply is set to 5 volts, and now he's gonna put the resistor.
This is a resistor right here.
This is a different resistor. I don't, I have never seen a resistor like that. But he's gonna connect this resistor to those two ends.
Pretty large resistor. It's a 20 watt resistor.
A very large resistor.
For 1/4 watt resistors, they're about this big right here.
Okay, that's the resistor that we usually use. Okay, remember that? The color codes here. And now
that is a 20 watt resistor.
That one resistor and another resistor. The resistor is huge. Can consume lots of power, this one here. What we usually do using our experiments is this type of resistors here.
Okay, difference in those. And this is a 3 watt resistor.
Another resistor.
In all sizes. There's much smaller resistors than any of those, called surface mount resistors. And those are more modern technology, like on this.
Yeah, that's another type of resistor. I want to.
Piece right there.
That's the surface mount resistor. There are all sorts of resistors out there in the market. Okay, if you're in the case of your cell phone, for instance, we use surface mounted resistors that are very small and can be plugged into this board.
The resistor, and you can see it's literally the size of the tip of the pen. And these are large. They're ones that are literally, you could stack 4.
Today with microelectronics, we can make very small resistors, by the way. You know, nanometric in size, micrometric in size, and even nanometric in size. With advanced technology, we are capable of doing that nowadays.
For 5 on top of this part right here. So things get really small. By this time in lecture, you probably saw that a power supply could be drawn in a schematic form as a circle.
Let's see, I wanna see him connecting the resistor.
Yeah, and there are two wires coming out. Have a ground wire.
Let's see, okay, he did that. Here you go, he's connecting the resistor. That's exactly the circuit that we are doing here in our lab. Just a circuit with a single resistor is the easiest circuit that you'll ever be exposed in your life. And we are going to use this circuit to find out, to demonstrate, to prove, verify Ohm's law. That's what we're going to do, okay? And how are we going to do that? Okay, put the circuit together. Here you go, here's the circuit, power supply, resistor, right? That's how we draw the circuit. That is the symbol for the power supply. The power supply that we use in the experiment, we start at 10 volts. I give you a resistor that you measure the resistance with it. And let's take a look at my, so here you go. Here is my spreadsheet. The same spreadsheet that you have out there, okay? Once we measure the resistor value with the multimeter, we log it right in here in the spreadsheet. Don't forget to put the units, right? Okay, this resistor here has 1197 ohms, 97.8 ohms. Make sure you display it with the proper significance figures. And we start with our power supply at 10 volts. Okay, 10 volts power supply. In the next step, we're gonna get our multimeter. Here go my multimeter. It looks just like that, the one that we have there at LA Harbor. Connect the red jack of the multimeter to the positive side of the resistor with one of those cables that you already saw. The black one goes to the negative side of the resistor, and you're going to keep on monitoring the voltage. If this power supply is set to 10 volts, your multimeter is going to read 10 volts in this case as well, because it's a single resistor. Measuring voltage, you see that? Measuring voltage. And you go ahead, you know, here V sub stands for the voltage of the supply, power supply. And we start with 10 volts. And we are going to decrease the voltage all the way to 2.8, for instance, and then invert the polarity and increase it back to 10 ohms, 10 volts. We are going to measure the voltage with the multimeter. Here we are measuring the voltage with the power supply. And here we are measuring the voltage with the multimeter. And we're going to measure also the current that goes through the circuit with the multimeter. Okay? That's what we're going to do. Here you go. Let's see, going back to my, connect the other end of the black cable to the remainder field. Your circuit is now ready to make measurements. Okay. Item 10 corresponds to this point here without the multimeter. At this very moment, we have a current flowing through this circuit like that. Electric charges are moving in this closed circuit. Okay, and we start our measurement by connecting the multimeter in parallel to the resistor. Voltage measurements always in parallel, always in parallel. Okay, and going back to our spreadsheet, here you go. That's the voltage. We're right in here. But first we're going to do these two columns, okay? Change the voltage. That's how we represent in a circuit diagram. Voltmeter, that's the symbol for the voltmeter. And then we change the polarity, so you can see a negative polarity in there. And that what this, here you go. We start with this one, change the polarity, and we see a negative value here in the reading of your voltmeter. Okay. Next, okay, and then you change to 8 volts, change the polarity. 6 volts, change the polarity, negative voltage. 4 volts, change the polarity, 2.8 volts, minus 2.8 volts. Okay, that's the first part. That's the first part of the experiment. Okay, the first in the first part of the experiment, you will measure the voltage across the resistor. From 10 volts to 2.8 volts. In the second part of the experiment, you will measure the current at each of the voltages. Okay, so the second part now, we're done with the first part. Second part, now we have to take the circuit apart. Okay, get the red cable, and now since we're measuring a current, we have to put our multimeter. We have to use our multimeter as an ammeter. And we use one of those yellow leads that we have there in the multimeter. The multimeter must be connected in series. That's why we have to take apart the equipment, okay? Red to yellow, black to the resistor. Resistor closes the circuit, and now this device will measure current. It starts at 10 volts. You start at 10 volts, we measure the current, right? Change the polarity, measure the current is going to be negative. 8 volts, measure the current, 6 volts, measure the current, and so on, okay? In this experiment, I first put the multimeter on this side of the circuit, and then I put the multimeter on this other side of the circuit. This circuit that we see here is what I call the I plus. We do that so you can see the measurements of the current are exactly the same, almost the same. Okay? So that's what I'm doing here. Here you go. That's how the diagram looks like. Okay. That's the first circuit to measure voltage. What's that? Okay, let's skip that. That's the circuit with the ammeter now inverting the polarity. Okay, and now we are going to measure the I minus. We're going to put the multimeter right here to measure current on this side. Okay, power supply, resistor, ammeter in series, but on the other side of the circuit. That's what I minus is all about. That's what the I minus is all about. And right in here is the average of those two values. Okay, here is the average of those two values. The power, you know, this, okay, and now the resistance using Ohm's law. So the next step, once we measure all the current values, we can plot our graph, okay? What's the graph they're gonna plot? Voltage along the y-axis versus current average current along the x-axis. Okay, and I will do that for you. Here you go. Okay, this one is gonna be a little bit tricky. I want, remember, the theory is something like that. Let me, I didn't write down the Ohm's law, right? Let me write down Ohm's law. Ohm's law is like that. V equal to Ri. Ri. I'm gonna plot I along the x-axis and V along the y-axis. That's what I'm gonna do. If I do everything right, we're gonna get a straight line with a slope equal to the resistance. Okay? So here you go. I and V. V1 in this case. Insert chart. Here you go. Now I have my graph, but it's not quite the right graph yet. Not quite the right graph yet because the voltage is along the x-axis and the current is along the y-axis. We have to invert this graph, right? So how do we do that? Did I teach you how to invert this graph? I can't. I cannot blow it up for some reason. Huh. Strange. Yeah. Man, this thing is misbehaving here with me. Oops, shouldn't be doing that. Let's see. Okay, now it's behaving the way I want. Good. So watch out. Here we have current in the vertical and voltage in the horizontal. We don't want that. We want the voltage in the vertical and the current in the horizontal. What do? Click one of the data points. Okay. Select data. Select data and edit here the series. When we edit the series, we just swap the G with the J. Okay. J here, and G here. Column J stands for voltage. Column J stands for average current. And now we have it the way we want. Okay, voltage, right? All the way up to 10 here. We can also have, don't forget to adjust. And then next, we are going to add the trend line, display the equation and the R square. Do you do that? Here goes the regression equation and the R square. And now what you're going to do, you're going to compare this slope here with the value of the resistor that you measured separately, independently, okay? You measure it separately or independently. What I got 1197. And your slope is telling you that's 1222. It's not much different. You're going to see that it's very small. You log the value 1222 here, and you're going to see that the percentage difference is only 2%. Very small. Okay, so this is sort of a successful experiment. Okay, and now you're ready to do the rest. Let's 11:03. Let's take our break again. Okay, plot once you measure, can plot our graph voltage along the y-axis and current along the x-axis. The resulting graph must be a straight line with a slope very close to the resistor value. Okay. It's 11:05:03 right now. Let's take a break from 11:05 a.m. to 11:20 a.m. Everybody managed to plot the graph? Let's see, just quickly here, one by one, right? That's the 20th. Attendance, plot graph. I'm gonna get, I go 7 plot. Let's see, Vanessa. Do I take attendance? Yeah, I did take attendance. Vanessa, did you plot your graph?
Yes, I did.
Okay, good. So let's get someone else here. Sky, did you plot your graph? Yeah. Yes, okay, good. And let's see, Paul, did you plot your graph? Yes, okay, good. So it's 11:05 right now. Let's take our break and we'll be back in 15 minutes. Okay, so here you go. I changed it a little bit here, the procedure, okay? I think it's better this way. You might want, once I posted it in there in Canvas, you're going to see that the procedure is a little bit changed, but it's a better procedure than what I went through with you folks. And now what you have to do, right? One, plot, right? V1, I'm gonna write that here. V1 along the y-axis, I average along the x-axis. I average is the average of I plus and I minus. So you have to worry about the significant figure here, right? Get the regression equation, right? And R squared. Log is slope of the regression equation in table. What table is that? In the last table. In the last table. Okay. And let's see what was the percentage difference that you got there in the last table, right? Percentage difference. I'm not gonna go through everybody. Jacqueline, did you get the percentage difference between your slope and the measurement of the resistor? Yeah. What did you get? What was the percentage difference that you got? .73. Oh, yeah, okay, yeah. Those experiments work pretty well. Very good, very well. Okay. In general, we get less than 1% of difference. So those experiments with circuits, resistors, and all those multimeters, those are mass manufactured devices. Because they are mass manufactured, we had plenty of time to fine tune all those instruments. And because of that, we frequently get less than 1% of percentage difference compared to the other experiments in mechanics, okay? So what about Norberto? Did you get the percentage difference to Norberto? And what was that? Still working on that? Okay. Did you plot the graph, by the way? So let's go here, back to the plot, to here. Did you plot the graph? Norberto? Yes? Okay, good. Do you have the regression equation and the R square? Yes, okay, good. Okay, so the next step would be to, so here you go, regression equation and R squared. Okay, so Norberto got that. So the next step is log slope, right? In the last table, you still didn't do that. You still didn't log the slope, Norberto? No, okay. Okay, so let's go for someone else here. Norberto is group 2, right? Let's go to Ashley is not here. Corina, did you get the regression? Did you plot the graph, Corina?
Yes.
Okay. Did you get the regression equation, the R square?
Yes.
Okay. Did you log the slope in the table down there?
Yes.
No?
Yeah, I did.
Ah, you did. What's the percentage difference are you getting?
I got 0.46.
Yeah, okay. Very small number. Anything. And by the way, you inverted the graph, right? Made sure you put the V1 in the y-axis and the I in the x-axis, right? Did you do that? Oh yeah, if you're getting 0.46, yes, you did everything right. Okay. You don't even need to answer that. Thank you. And let's see who else I want to talk to. Let's go for Yorgo. Yorgo, did you plot the graph?
Yes.
Okay, did you get the regression equation, the R square?
1 second, I'm checking. Hmm. Is this in the data and results? Where is it?
I want you to display the R square. Here you go, just like I did. See, you got something like that, right? You got a plot like that, right?
Yeah.
You get
We did
the
we did the
regression.
graph. Let me check. Yeah, we did. Yeah, we
Okay,
did the graph.
the regression equation, the R square. Okay, so the next, did you log the slope in the last table?
Check the last table. 1 second.
Okay.
Yeah, we did it.
Okay, what percentage are you getting? Here you go. Here's the slope, where the slope goes, right? What percentage difference do you
For
get?
which one? The single, the series, or the parallel?
Oh, you log the slope in this table, right?
Uh, yeah. There's one
Oh,
second. If I go with mine, for mine, there's 3.
3%
There's the slope and there's a difference.
percentage difference. So you got 3%?
Yeah,
Is that
zero. The difference was 0.351.
0.351? Okay. 0.351. Okay, good. Thank you. Now let's see who else. Now, well, let's get Paul Zapata. You get the regression equation, Paul, in the R square.
Yes, I did.
Okay. What about, did you log the slope as well in the last table?
I believe I did. I got the percent difference I got was I think the same as your goal.
Yeah, you're supposed to get the same value as this.
Yeah.
Okay, so the last table, just to remind you, right, is this one right in here, right? You get the slope from this regression equation and you log it right in here. And whatever number you get here is your percentage difference. Okay, so 30. Now, let's see. Who else? Ashley is not here today. Okay, let's talk with Vanessa. No? Hi, Vanessa. Did you get your regression equation, your R square?
Yeah,
Okay, good. You log the slope in the last table?
yeah.
Okay, what's the percentage difference you're getting?
Mine shows 1.72.
1.72. Okay, that's a very good percentage difference. And I still didn't talk to Lizelle, right? Hi, Lizelle. Did you plot the graph? Lizelle is not here. Oh, that's not good. Left. Okay. Okay, I'm gonna put like half here. No, that's for Yorgo. Yeah, oh yeah, no. That's Lizelle. Okay, good. So what time is that? 11:30. 11:30. Good. So what else you have to do? There's more stuff that you gotta do. Log the slope of the regression equation in the last table. Report the percentage difference. Percentage difference, which is usually less than 5% for this type of experiment. Once we are done with that, then work on the units, right? Units. All the units go here. Don't forget unit, right? No units here. Oh, you must have units here and here. No units for those, right? And after the units, work on the significant digits. Okay. What you have to do? No. Change the font, the format of the number when necessary. When necessary to change, when necessary, right? Adjust the number of decimal places, right? So I'm going to those numbers, those numbers are more than 1,000, so you can put them in numeric format. And then you have to adjust. And by the way, here, you must also worry about the significant digits, okay? VSUP has, let's see, here you go. VSUP, see, for the power supply, you are going to have to display the right number of significant digits depending on the value that you get for VSUP. If it's just above 10, it's going to be what? 4 significant figures, right? Get this one out of here. No. 4 significant figures. So this up here, this guy here, I have to display with 4 significant figures. 4 significant figures should be 2 decimal places. Here and here. Now, what about for the other values? Between 1 and 9.99 is 3, right? They all should be 2 decimal places to result in three significant figures. And then for V1, that you get from the DMM. That you get from the DMM, this table here. Voltage DMM, voltage of the power supply. Those are two different instruments. That's why they end up having different significant figures, different numbers of significant figures. Right? Let's see more here. Oh, don't show. That is, yeah. Anything in red does not require significant digits. Anything in red that is slope doesn't need significant figures. It's percentage difference. You don't have to worry about significant digits. Quantities in red do not require significant digits. Okay. After significant figures, then determine the CL. The more difficult we leave for last, right? And don't forget to fill up here as well. Any question? Let's go through the class again. Let's see, Sky, did you get the regression equation, the R square? Yes, okay, good. Did you log the slope in the proper place? Yes. And the next one, what's the percentage difference you're getting? Point 0.5? 0.5, okay, which is the same as Corina, right? Okay, good. Here you go. Ashley is not here, right? Let's see, Norberto, did you log the slope, Norberto? The table? Yes, what's the percentage difference you're getting?
I got 1.72.
1.72? Okay. Okay, now the rest is just the units, right? Units, sig figs, and CL. Units, sig figs, and CL. Any question that you may have? Well, it looks like we're finishing earlier again. I need to start spending a little bit more of time with the lecture, right? So you don't go, we don't leave earlier. But let me brief you quickly. Here, going back to the lecture. Going back to the lecture, okay? All the above, recall that, recall that I told you that the magnetic field, right? The magnetic field of different current distribution. These magnetic fields can be obtained using using Ampere's law. Ampere's law, okay? And Ampere's law is, recall, okay, what I'm going to, yeah, okay. Ampere's law is given by the following. Law given by the following equation. This one here, you have to memorize that. Just to remind you, right? The equations for the other laws, right? Are those here. That's for the electric flux. The electric flux is written like that. The magnetic flux is written like that. It's the same equation, but we will replace the electric field with the magnetic field. On the right side is 0 because there's no source for the magnetic field, right? Now, the new law now is rather sort of similar to the other two, right? Kind of. So what are the similar, the new law, the Ampere's law? Okay, in the case of Ampere's law, we have a B field here, and we have a B field here. The difference here is that this B field is to calculate the flux. But, the flux, I know it's the flux. Why is the flux? Because we have an area here. But here we do not have an area. Here we have something else other than the area. And we are going to elaborate it a little bit more, okay? It's by using this equation here that we find those results that we saw for the solenoid and the infinitely long wire. Okay? And note also that we have our source here, source of magnetic field, right? And if we go back to the Gauss's law of electricity, we also have our source here. I'm putting them in red boldface. Okay? But don't forget, because it's a flux, we have an area here. Whereas here is not an area, here is a path, and I'm going to elaborate on that next time. Okay, so I think we can stop now. Do you have any questions? So I see you on Monday, and now I'm gonna have office hours until 12:45. Okay? I see you again Monday.
Professor, do you know when you're going to upload the rest of the recordings onto Canvas?
Oh yeah, I'll do that today. I'm a little bit
Okay.
behind, right? I'm a little bit behind. Sorry, but yeah, I'll do that today.
Okay. Thank you. Have a
Now,
great
do
rest of
the
your day.
recordings help? Do the recordings help?
Yeah, I like to go back and rewatch them.
Huh? What do you say?
Yeah, I think they help. I go back to rewatch them.
Oh, that's nice. Okay, that's great.
Yeah.
Thank you. I will, I will try to make it better. I don't do any editing on that. It's too much work to do the editing, but I'm gonna start doing the editing to. Hopefully, it's gonna be better. Gonna be easier to watch it. I'll try to put closed captions, things like that. Okay.
Okay. Thank you.
Thank you.
Bye-bye.
Bye-bye.